Well, welcome back to our office, and we shall continue our discussion of waves today, probably the last time for a while until we get to water waves. And today we'll talk about solving a particular set of partial differential equations, the Maxwell's equations, which you've known and seen other places. If you've never seen Maxwell's equations, you should go look at them before we cover them here. And for our purposes here, what's interesting is we now will be solving a wave equation, or a series of equations which produce electromagnetic waves, and these are coupled waves. So they're vectors, electric field, magnetic field, and they're coupled vector waves. So they're much more complicated waves in that sense, although the technique is much the same as all other wave equations. So the method we'll use will be the standard finite difference approximation. We'll solve it on a grid, as we did all before. So we won't spend much time on that. But in the field, colloquial physics talk, this is known as the finite difference time domain. So it's finite difference in both space and finite difference in time, as all these wave equations are. But for whatever the reason, it's known as the FDTD method. So if you see FDTD, usually refers to solving Maxwell's equations. But it really is the same for every wave equation. So look at slide number 2. You're given a problem. And the problem says, determine, bold, meaning vector, determine the vector electric field and the vector magnetic field for all times in some region of space varying from z values of 100 to 200. So, it's a real problem. There's a hint here, of course, which is if they're only telling you the region of space where z is, probably there's only a z variation which occurs, okay? And so that's the problem. You're given the initial conditions. So the initial conditions are similar to this sketch, which is just a sketch. It's not a real plot. But you're told that initially at time 0, there's an x component of the electric field with some sinusoidal variation in space. And then there's a y component of the magnetic field with the same sinusoidal variation in space. So what you're seeing here is we're starting up initially with a wave E in the x direction, as we show up here in red. Okay? So it varies only in the x direction, or at least the electric field has a component only in the x direction initially, and it varies throughout all the space sinusoidally like this. So this is, of course, in a sense, t equals 0, what the initial condition is. The y component is of the magnetic field, so it's a different field whatsoever, and it varies along the y-axis sinusoidally. So that's the initial condition. And what we'll know from Maxwell's equations, you use the right-hand rule, E cross H will tell you the propagation direction. So this bold arrow represents either time moving forward or the direction of propagation of the wave. Okay, so we'll see that. So, that being said, this is an important subject. Electromagnetic simulations have tremendous practical implications and many applications. Practical devices, electronic devices, at the moment, nanotechnology, spintronics, they all solve these equations in much the way we talk about here. We don't require you to go out and buy a separate package. We'll just give you a simple algorithm to solve it. Some people go out and buy packages to solve it even better, maybe for more complicated geometries. But it's really a pretty straightforward technique. It can even be solved with a simple Excel program. Many cases do it. But we have various codes. So it's really quite simple, even though the applications could be very complicated. So again, it's a wave equation, no big thing. We'll solve it on a grid. We'll use time stepping or leapfrog method. We now have coupled fields, which make it a more complicated problem, but basic algorithm is still simple. And we suggest you look at the references if you want to see some of the applications. It's a very big field. You can get more and more involved, but you should be able to understand the basic physics quite easily. So please, take a look at the next slide. What is the theory? What's the theory for electromagnetic waves? Maxwell's equations. You could put it on your t-shirt. Probably right here is Maxwell's equations as well, if you want. You know, they're always there, right along the top. Okay, so Maxwell's equations. On the left-hand side here, you see in bold, meaning vectors, again, these are the 4 vector equations. For the problem at hand, when we only have an initial E field in the x direction, we'll keep an initial E field in the x direction. No others would exist. So the del dot E becomes the derivative of E sub x with respect to the x direction. Del dot H becomes derivative of H sub y. So this is the only component which matters. And the time derivatives here, time derivative of E, which is the x component of E, related to the space derivative of the z space derivative of the y component of H. And likewise, the time derivative of the H component of the y component of H is related to the space z derivative of the x component. So that's a lot of sort of complicated words, and that's exactly the point. This is one of the nice things about E and M and doing the simulation, which is you see which fields drive the other fields. Okay, so we'll have to solve these problems, and that should come out. But this clearly is now 4 coupled partial differential equations. It's one-dimensional in the sense that the propagation is just in the z direction, so there's just one-dimensional propagation. But then it actually is a 3-dimensional problem because the x field is in one direction, the x direction, the E field rather. The H field is in the y direction, and the propagation is given by, for a transverse electromagnetic wave, E cross H is along the z-axis. So it's throughout all of space. You obviously can change the axes, have even more complicated equations, but that's all we need. So, where are we? We need to solve these simultaneous 4 equations. There's just 2 unknowns, if you want, E sub x and H sub y. All the other components are unknown. And as before, it's sort of obvious, there's a simple time derivative here. First time derivative, first space derivative. So it's a different wave equation. These give you electromagnetic waves, so this isn't a wave equation. At least all 4 together are. And so, since we just have a simple time derivative, this time stepping will work because the time derivative finite difference just relates present and future, and that's all we need to predict the future. Space derivatives indicate different places in space. What's complicated is we have 2 different fields in different directions, but the algorithm, they're just different components of a vector of something. So let's go ahead and look at the kind of algorithm we want to solve. So take a look now, and you should, because this is more complicated. Take a look at the next slide. And what we have on the next slide is the same 2 coupled equations, or Maxwell's equations we've put together here in the central difference approximation for derivatives in the discrete form. So these are the 2 coupled equations we need to solve. We see that the time derivative of E determines the space derivative of H. The time derivative of H determines the space derivative of E. That's good. And now we have, in actuality, we have 2 interlaced grids, if you want. It's another time staggered technique, except here we're staggering not just time, we're also staggering space. Whew. So we have E sub x, or the E field, is being solved on the grid which is filled points. So the red fillings here is where we solve the E field. And the H field is solved on a grid, the lattice, at the open points, little white centers. Okay? And so that's at x over 2, and the E field is solved at time t over 2. So we have 2 displaced grids. Why do we do this? I don't know, I guess just to make life complicated, but we do it in order to reduce errors. Okay? You need to relate the field, you want to cancel off some of the errors, so we can use a very simple derivative expression and still have fairly high precision. So you have to go through the numerical analysis to see that the derivatives cancel, but other than that, it's pretty straightforward. So here's essentially the same algorithm, and we can go back here, and what we have first here, this slide, is we have the derivative expressed on the left-hand side, the time derivative, and then we have to write this down as an algorithm to go ahead. Go ahead and predict the future wave from the present wave. So we do that on the next slide, and what you see here is, okay, we've just moved things around, so we have a prediction again, and so we have here, we have a whole bunch of coordinates. The subscripts are easy. They're just giving the direction of the vector, fine. And the superscripts are space and time. So this is now, k is not changing here, so obviously this is a space coordinate, which is z, and this is the time coordinate, t, and this is saying time one step ahead, this is one step behind, this is now another vector also at the advanced time, and this is a vector at a different time. So we need to solve for that as well. This is a little more complicated. Okay. Likewise, here we have for the h component, k plus a half, just what we need over here. That's given in terms of a component at the same time but a different place, and likewise other times. Okay, so we have these coupled equations. We need to solve them. The k refers to this integer space step, which is in the z direction. N in these equations refer to the half integer time step. So this is n going ahead here in space, in time rather, that's what we need. Here, future, a half step behind the past, a full step behind the past. So there's a bunch of times involved because they have different e's and h's. Okay, we've said this before. The time derivative of E determines the space derivative of H and vice versa. So it's again a time stepping algorithm, but we now have two vector fields at different space points, at different time points put together. So let's look at the results. Very simple algorithm, easily done. Here's our algorithm. In practice, we try to make the algorithm simpler by rescaling the electric field so that the E field and the H field have exactly the same dimensions. So if you look at the previous algorithm here closely, you see there's delta t over epsilon 0 delta z, and here it's delta t over mu 0 delta z. And some of you will recognize, of course, the ratio epsilon 0 mu 0 is just related to the speed of light, the wave propagation speed. So if we actually rescale the E field by just the speed of light, the square root of mu 0 over E 0, we get two coupled equations with the same coefficient out front here, very nice, and one coefficient only. So here's our equations. We can get, again, we go ahead in time, behind in time, behind in time, behind in time. So it's again just stepping us forward in time. Beta is just a constant, and it's just like we've seen in other waves. It's the wave propagation c, which in this case is the speed of light, and then this delta z over delta t, which is like the algorithmic speed, propagation speed, and c, of course, is just the square root of epsilon 0 mu 0, the speed of light. And so we want to choose delta z and delta t when we apply this algorithm small in order to be accurate. But we have to always be careful about stability. As you've seen the Courant condition before, it's usually the ratio of two velocities determines stability. The same is true here. So we want the x scale, the space scale, to be something like less than 1/10 of a wavelength. So what's the wavelength? Well, we tell you from the initial conditions, you know what the wavelength is of the wave we're trying to simulate. That determines what your space grid should be. And once you have the space grid, you want the time scale to be set by the frequency, whatever frequency the wave is propagating at. That tells you how many oscillations per second you want to get all those oscillations in. So you have to have a small time step to see all the oscillations. That, of course, has to also be congruent with the Courant stability condition. So in this case, the stability condition is that this ratio, beta, which is just C divided by delta Z over delta T, it's just this multiplicative factor in the algorithm, that has to be less than a half. So you can't just make delta Z smaller and smaller without simultaneously making delta T smaller and smaller. So that's almost always the case. You know what delta Z should be. You know at grid in space where you want the electric field to fit your apparatus. So you have to then make delta T small enough, typically very small, so that this condition is still met. So what happens? So we have lots of codes we can give you here. We have, let's talk about the code. The code is a finite difference time domain code. It's just the same space-time lattice as before. We start off with 200 sites. That seems to be enough to get going. Maxwell's equations, the algorithm, if you look inside the code here, and I won't show you that now, the algorithm just takes you, even though we talked about these split time steps, that's all in the theory of the algorithm. The way we write the algorithm down, we start off with some time 0, let's say, the initial time, and then we move to the future 1. And then we just interchange present and future. So these, if you go back, these correspond to different half-size differences, but we only solve and keep these 2 times. So you have to know ahead of time what the 0 and 1 mean. So that's what they mean. And this is just our algorithm. The time derivative of E determined by the space derivative of H. Time derivative of H determined by the space derivative of E. So if we look at the algorithm, we see that this works except the endpoints corresponding to k equals 0, k equals the max minus 1, they're still undefined. We have to do something about boundary conditions. Remember, the problem just gave you those pulses and said, what happens? Well, what happens is the pulses propagate. Okay? But what happens when they hit the ends? What ends? Well, you can't solve a partial differential equation without specifying the boundary conditions. In order to have a unique solution, if you remember, there's that chart we showed you here, we showed you in the book, you have to have the boundary conditions specified. If your problem doesn't specify your boundary conditions, then it's up to you to do it. And you can do it either in any way you want. Hopefully it doesn't matter, at least on the interior region. So one way is to assume periodic boundary conditions, so the waves just keep coming around and around. The other way is to assume boundary conditions which the wave function or the wave packet has to vanish at the ends. Then you get standing waves. So you'll do both. So here we assume periodic boundary conditions, in which case at the max, we're just making the max equal to where we started. So let's take a look at what happens here. So here we have one of these codes, and I think I have the code running on another machine here, which we haven't brought over. So okay, so that was our 2 pulsars running. It almost runs too fast to see. So there is the this is the E field pulse moving along, and that is the H field. If we look at the if we put them together and look at it and make an animation, you see here, and you can see little flashes as it's moving along. This is the propagation in time for our problem. Okay? So this is a code. It's on the DVD. It's on the web. This is the Python code. This is the simulation, and it works just as expected. These are waves. The pulses are propagating. So what we're saying is, you start off with a pulse over space. You let go. It's just going to continue and propagate throughout all the space and time. So we'll stop these. Let's go back to work here. Okay, so what's for you to do? Get to work. We're giving you a code, or you can write your own. But this is complicated enough you may want to write your own based on ours or use ours. Take the code. First thing to do is impose boundary conditions. periodic boundary conditions, or try, I think we give you periodic boundary conditions, so try imposing 0. Make the ends nodes. Look at the effect. See if you can determine where in space the boundary conditions are affecting the solution. Before they hit the wall, what happens after they hit the wall. Always look at stability. Test the Courant condition. Make delta Z small as you want. Don't change delta T. Things should blow up. See that, in fact, it works as expected. Then extend what we're doing. Do something interesting, saying, okay, we have our solution in space-time. We've drawn that here. So this is X, Y, this is Z. What if we have in this region here a block of some sort, a dielectric block that the wave has to travel through? You can make it square, okay. And it could be a filter. It could be a comb, okay, something like that. Look at the reflections at the boundary and the interior boundaries. See what happens to the wave when it hits a dielectric medium. Try varying the index of refraction, n, of this medium and seeing what the effect might be. And likewise, we'll see at the end, if you make the medium with a periodic permittivity, like a comb, you actually get a filter. So try first putting in the index of refraction. Check, and this is something else, check different initial conditions. Start off, for example, with just a pulse, electric pulse, no magnetic field pulse. What's happening? Well, what you'll find is that, interestingly enough, you no longer just get simple propagations with space. You get pulses coming out the right and the left. Okay, so it's different initial conditions give you different solutions. Look at the answer. Is this all consistent with E cross H, giving you the direction of power flow throughout? Finally, see if you can change the propagation direction. Okay? So the phase of the initial electric and magnetic fields determine what direction the wave propagates in. Try phase differences of 0 and pi. See if that changes the propagation direction. Okay? You have a simulation. Play with it. Use it as an experiment. Now, particularly, explore those resonator modes. In other words, if you make the electric magnetic waves vanish at the endpoints, then it's like having an electromagnetic resonator or waveguide. You should get a standing wave pattern. See if that works. These are more complicated waves. It's not obvious. See if you can set up a standing wave with a wavelength greater than the integration region. What happens? And finally, we give this as an optional. If you have that medium inside here, this dielectric medium, what if you make the medium periodic? Okay, what if you make the index refraction periodic, like a comb? You should then have a filter, see if it filters certain frequencies and not others. So the number of applications here is just endless. Take our code, use it yourself, change it off, read the references, whatever. No longer are you restricted to having to do very long analytic solutions for Maxwell's equations. Numerically, once you have that simple algorithm, you can solve various geometries, various permittivities, various practical devices are all within your realm. So go ahead, go out and get jobs and enjoy it. Bye-bye.